Hi, I'm Curt Frye. In this movie, I'd like to show you how to implement a simple traveling salesperson problem in Excel. The sample file I'm using is called TSP Setup, and you can download it from the link that I have provided in the video description below. I have two worksheets, and the first one just has my data and formulas as well as a chart that will show you what the station locations represent in terms of visual space. And then we'll switch to sheet 2, which is where we will actually create our solution. So I'll start on sheet 1, and I have the locations for 8 different stations. So those are stations 1 through 8. And then I have the locations as for their XY coordinates. And if we take a quick look at the map, we'll see that station 1 is here. The location is 13X and 17Y. And if we scroll back up, that is what I see in row 2. And the sample map gives us a hint just by looking at it as to what the likely shortest path will be. I think that it might start at 1, then go up to 4, to 3, to 6, to 2, then probably to 7, 8, 5, and then back to 1. And in fact, it's usually possible with a short trip like this to determine the shortest route just by looking at it. However, if you need to do math, then you can create what's called a distance matrix, and that's here. And what this gives you, with the help of this extremely long formula that I won't go into detail here, but will in a subsequent video, uses the Pythagorean theorem to determine the distance between 2 points based on the square difference of the x and y coordinates and find the square root of that. So what's happening is that a squared plus b squared equals c squared gives us the distance. So I have a distance of 0 between 1 and itself, which makes sense. Same for 2 and 2 and 3 and 3. If we want to determine the distance between station 1 and station 2, we can go to the first row and the second column and see that the distance is 21 units. And I have used round up to go up to the next integer value. And because this is a symmetric matrix, in other words, we assume it's the same distance or time either way, then going from 1 to 2 is the same as going from 2 to 1. So 21 and 21, and then from 1 to 3 is 40, 3 to 1 is 40, and it's the same for all of the other distances. And once again, the map tells you where things are in space, and it allows us to use our intuition to verify the solution that we get is probably correct. So let's switch to sheet 2, which has the same distance matrix, and start creating our solution. We have 8 stations, so that means we need to have a path that includes each one of them. So here's how we do that. I'll start in cell B11, and this will be one of our variable cells, and type a 1, and tab to move to the right, and then 2, tab to move to the right. Now I'll select cells B11 and C11, and drag the fill handle to the right until I cover I11 so that I get the values 1 through 8. Now in cell C12, I can calculate the distance from 2 to 1 by looking up the value in the distance matrix above. And we can do that using the index function. So I'll type equal index. And the tooltip that appears indicates that index returns a value or a reference of a cell at the intersection of a row and column in a given range. So we have 8 rows and 8 columns, so I can specify the column number and the row number to get the distance between 2 stations. So I have index. The array is B2 through I9. And because I'll be copying this formula over, I'll press F4 so that the reference is entirely absolute. No changing rows or columns, then a comma. The row number will be the value in B11, then a comma. The column number will be the value in C11. And again, because this is a symmetric matrix, I could do C11 or B11 first, just so long as I have the other one in the second position. Then I'll type a right parentheses and press tab, and I get a distance of 21 going from 1 to 2. And I can look up row 1, column 2, and see that that is the correct value. And then I will click cell C12, grab the fill handle, and drag to the right. So I now have 7 distances. However, I need to go from 8 back to 1. So what that means is that I need to have this value, which is currently in B11, and this could change. It won't always be 1. Here in cell J11. So I'll type equal B11. And this allows us to go from 1 all the way through to 8 and back to 1. And then I just need to copy over the distance formula. So I go from 8 to 1, and if I go from 8 down to the first row of 1, that indeed is 12. So the lookup is correct. Our goal is to minimize the total distance traveled. So in cell D14, I'll type equal sum, and then get the sum of the range C12 to J12. Right parentheses and enter, and there is the current total. Now we can set up a solver model that will find, or at least try to find, an optimal route. So let's go to the Data tab on the ribbon. And in my version of this workbook, I have Solver already installed. If you don't see Solver in the Analysis group, then go to the File tab, click Options, then click Add-ins. Make sure that Excel Add-ins appears in the Manage box, so you can click the list arrow if you don't see it, and click Go. And then ensure that Solver Add-in is checked, and click OK. In this case, I'm not changing anything, so I'll just click Cancel. That looks good. And then back on the Data tab, I will click Solver. And I've already entered my Solver parameters. So instead of talking through it, I'll actually let you see me do it. So I'll click Reset All. Reset all of it, click OK, and there we are. The objective cell is the cell we are trying to minimize or maximize or make reach a specific value. So I will make sure that the insertion point is flashing in the Set Objective box, and I will click cell D14. Again, that's the sum of all of our distances. I want to minimize that value, and we'll do it by changing the variable cells that I have highlighted in yellow, which is a practice that I use to indicate which cells will be changing. So I'll click the Collapse Dialog button, and then select cells B11 through I11. And remember, J11 is equal to B11, so we don't need to include that in the variable cell list. It's already there. Click the Expand Dialog button. So I've got B11 to I11. And now I can add my constraints. I'll click Add. The first constraint will be to ensure that cells B11 through I11 are all greater than or equal to 1. So with the insertion point in the cell reference box, B11 through I11 greater than or equal to the value of 1. I'll click Add. And then the same cells need to be less than or equal to 8, which is the highest number that we have for a station. So that will be B11 to I11 less than or equal to 8. There we go. Click Add. And the final constraint is one that you might not have created before, and that is to ensure that all the values from B11 to I11 are different. And if you didn't know you could do that, well, now you do. So I have the cell reference, B11 to I11, and then the middle has the diff keyword. So that will be the comparison operator. So I have diff, the constraint is all different, and I'll click OK. The next thing you need to make sure to do is to select the correct solving method. So next to select a solving method, be sure to set to evolutionary. The other options are GRG nonlinear, which is usually what you'll see solvers set to, simplex LP, which is definitely not what we want, and then evolutionary. So I'll click evolutionary, and to ensure that it works, given our setup, I need to click Options. In the Options dialog box, go to the Evolutionary tab, and the one thing that you need to check is to ensure that Require Bounds on Variables is checked. So make sure that checkbox is checked, and then click OK. And you are back in the Solver Parameters dialog box. And now we can ask Excel to use the evolutionary engine to find what we hope will be an optimal or near optimal solution for our network. So I'll click Solve and let the process run, and I will be back when it's done. If you look at the bottom left, you can see the process running. We have the current best value called the incumbent, which is at 125. And then we are coming up on our 40,000th subproblem. So it's going through them very quickly. So hopefully, within a few more seconds, it should stop and let us know what solution it has found. There we are. And it looks like 125 was the best solution that I could come up with. So I'll click OK. And the solution goes from 1 to 4 to 3, 6, 2, 7, 8, 5. So 1, 4, 3, 6, 2, 7, 8, 5. Let's see what that looks like on the map. So go from 1, 4, 3, 6, and then what was the next one? 2, 7, 8, 5. So that is, in fact, the path that we guessed was probably the best solution. And just because it fits what we thought it would be doesn't mean it's absolutely correct. However, it does seem like it's a good approximation. So that's it. It's actually a fair amount of work to get this type of traveling salesman problem set up. However, once you do, you are able to find the optimal route for a particular day, and that can help with your delivery time. It can help visiting customers effectively, and also, if you're dropping kids off after football practice, that will work as well to find the best route. I hope you enjoyed this video. There will be several more on this subject. If you did, please like the video and subscribe to my channel.